Okay, howdy partners, and welcome back to episode 7 in our series looking at advanced higher physics past papers, and this time it's the turn of general relativity. What could I get asked about general relativity, you might ask? Well, there's a very useful document called the SQA Advanced Higher Physics Course Specification, and that tells you everything that is in the course and everything that you might get asked about in the final exam. So there's the general relativity content statements, and notice it's knowledge, 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 and one little relationship at the end about the Schwarzschild radius of a black hole. So with that in mind, let's have a look at a couple of past paper questions, and the quickest way to do that is to use Mr. Davies' interactive PDF of Advanced Higher Physics past papers by key area. And thanks very much to him for this fabulous resource. So there's the general relativity questions. There's 1, 2, 3, 4 of them in the past 5 or 6 years. So let's firstly have a look at 2018, and it's question 5. So question 5a, explain what is meant by the term Schwarzschild radius. So we could go straight to the content statements for the answer for this, and there it is. It's knowledge that the Schwarzschild radius of a black hole is the distance from its centre to its event horizon. So let's just pop that in. Distance from the singularity to the event horizon. And of course the singularity is the centre of a black hole. There's the MIs. Now, our answer is the bottom one of those statements. The Schwarzschild radius is the distance from the centre of a mass to the event horizon, although we've answered it in terms of a black hole. But it is an explain question, and that first answer there is probably a more detailed explanation in terms of the Schwarzschild radius relationship. It says the Schwarzschild radius is the distance from the centre of a mass such that the escape velocity at that distance would equal the speed of light. But both responses there are acceptable. Part B, calculate the Schwarzschild radius of the Sun. Well, any object can have a Schwarzschild radius. We just use the relationship and substitute in for big G, which is 6.67 times 10 to the minus 11. The mass of the object, which is the Sun in this case, we'll get the mass of the Sun on the data sheet. There it's there. It's 2.0 times 10 to the 30 kilograms to two significant figures. And we'll also need the speed of light, and notice the speed of light on the datasheet is given to 3 significant figures. So let's put both of them into that relationship. So mass of the Sun and the speed of light to 3 significant figures. And then if you do that in your calculator, you'll get an answer to 2 significant figures of 3.0 times 10 to the 3 meters. And the reason it's 2 significant figures is because we always go with the lowest level of precision of the data in the question. And in this case, that was the mass of the Sun, the 2.0 times 10 to the 30. Anyway, there's the marking instructions. Straightforward 3 marker, equation, substitution, and final answer with the correct units. B part 2, explain with reference to its radius why the Sun is not a black hole. Well, the radius of the Sun we will also find on the datasheet, and there it is on the left hand side. It's 6.955 times 10 to the 8 meters. Interesting that we know the radius of the Sun to 4 significant figures, but only its mass to 2 significant figures. Anyway, the Schwarzschild radius of the Sun is 3 times 10 to the 3 meters. Therefore, because the Sun's radius is greater than its Schwarzschild radius, then the Sun is not a black hole. There's the MIs. Sun's radius is greater than the Schwarzschild radius. Okay, part C. The point of closest approach of a planet to the Sun is called the perihelion of the planet, and the perihelion of Mercury rotates slowly around the Sun as shown in figure 5a. Lovely diagram. And this rotation of the perihelion is referred to as the precession of Mercury and is due to the curvature of space-time, and this causes an angular change in the perihelion of Mercury, and this angular change per orbit is calculated using this relationship. Now, you've never seen this relationship before, so this is the unfamiliar relationship question. And all you have to do here is take the numbers that you're given and put them into the relationship and work out the quantity that's required. And in this case, that's the angular change in the perihelion of Mercury after 1 Earth year. Now, in this relationship, that little Greek letter phi is the angular change per orbit. And we're also told that after 1 Earth year, Mercury completes 4 orbits. So what we're going to have to do is work out what phi is and then multiply it by 4. So let's write down the relationship again, and we'll multiply both sides by 4. So 4 phi will be equal to 3 pi times the Schwarzschild radius. Well, we worked that out in the previous part of the question. It's 3 times 10 to the 3, or 3.0 times 10 to the 3, and we're told that A is 5.805 times 10 to the 10, times 1 minus E squared, and E is 0.206, and remember that's times 4 because it's 4 orbits in 1 year. And so therefore the angular change after 1 Earth year is equal to 2.0 times 10 to the minus 6 radians. And we're given our answer to 2 significant figures. And the reason that it's 2 significant figures, even though we've got 4 sig figs and 3 sig figs and 2 sig figs in the calculation, if we go back, the Schwarzschild radius was calculated to 2 sig figs. And the reason for that was because the mass of the Earth was to 2 sig figs. Remember, your final answer should always have the same number of significant figures as the data with the least number of significant figures in the question. Significant figures are always tricky. So there's the marking instructions. 1 mark for subbing all the values in, 1 mark for remembering to multiply by 4, because there's 4 orbits in a year, and 1 for the final answer. There will always be a number of questions in the paper with relationships that are unfamiliar to you. But remember, all you have to do is put the numbers in that you're given and work out the quantity that is required. Alright, let's have a look at another paper. This time it's 2016, and we're going to have a look at question 5. So Einstein's theory of general relativity can be used to describe the motion of objects in non-inertial frames of reference, and the equivalence principle is a key assumption of general relativity. And for part A, we have to explain what's meant by the terms non-inertial frames of reference and the equivalence principle. So firstly then, part 1, a non-inertial frame of reference is a frame of reference that is accelerating. And part 2, what's meant by the term the equivalence principle, well, straight from the specification document, the equivalence principle states that the effects of a constant acceleration and a uniform gravitational field are indistinguishable. There's the marking instructions for those two. And so I suppose it's a case of making sure you learn your definitions there. Okay, part B. 2 astronauts are on board a spacecraft in deep space, far away from any large masses, and when the spacecraft is accelerating, one astronaut throws a ball towards the other one. And on figure 5A, we've to sketch the path that the ball would follow in the astronaut's frame of reference. Well, we've just stated that the equivalence principle states that the effects of gravity and accelerated motion are indistinguishable, so the path would just look exactly the same as a ball thrown in a gravitational field. So, projectile path, downwards curve. And 5B part 2, the experiment's repeated when the spacecraft is travelling at a constant speed. Sketch the path the ball would now follow in the astronaut's frame of reference. So, constant speed, 0 acceleration, equivalent to 0 gravitational field. So, straight line, and in fact, any straight line. And then 5 part C, a clock is on the surface of the Earth, and an identical clock is on board a spacecraft which is accelerating in deep space at 8 meters per second squared. And we've to state which clock runs slower, and justify your answer in terms of the equivalence principle. Well, the gravitational field strength, or acceleration due to gravity at the Earth's surface, is 9.8 meters per second squared. So the clock on the Earth's surface will run slower because 9.8 is greater than 8 meters per second squared. Or in other words, the general relativistic effects will be more noticeable in a greater gravitational field, so the clock will run slower. And there's the marking instructions. One mark for saying the clock on the surface of the Earth will run more slowly, and the second mark for saying the effective gravitational field for the spacecraft is smaller. So, two very different questions on general relativity, very little calculations involved, a lot of explanations and statements, all based on those content statements in the specification document. Usual story, you want to get a lot of practice on past papers, use Mr. Davies' interactive PDF if you want to focus in on key areas. And in the next one, we'll be looking at the last key area in Unit 1, and that will be in stellar physics. And we'll see you in the next one.